Imagine you have 10,000 student names and their marks. Now you need one student's marks right now. Would you really check every record one by one? There's a data structure that finds it almost instantly, no matter how big the list gets. It's called a hash map, and by the end of this video, you'll know exactly how it works. A hash map stores data as key value pairs. The key is what you search by, like a student's name. The value is what you want to find, like their marks. So Amit maps to 92, Priya maps to 88, Rahul maps to 95. Give the hash map a key and it hands you the value, fast. The magic is in how it finds it. Let's open it up. Inside, a hash map is surprisingly simple. It's basically an array of buckets. Here's a tiny one with 5 buckets, numbered 0 to 4, all empty for now. Arrays are fast because if you know the index, you can jump straight to it. So the real question is, how does a name like Amit turn into an index like 0? That's the job of the hash function. A hash function takes a key, any key, and converts it into a number. Feed in the text Amit, and out comes something like 12,345. But our array only has 5 buckets, so we take that number modulo 5, that's the remainder after dividing, and we get 0. So Amit belongs in bucket 0. And here's the crucial property. The same key always produces the same index. That consistency is what makes everything else work. Let's insert our first entry. Put Amit 92. Step 1. The key goes through the hash function. Step 2. We get index 0. Step 3. The entire key value pair is stored in bucket 0. Notice we store both the key and the value. That detail matters later. That's insertion. Now, the part hash maps are famous for getting data back out. To get Amit's marks, the hash map doesn't search at all. It hashes Amit again, gets the same index, 0, and jumps straight to that bucket. It checks the key matches and returns 92. No scanning, no comparing thousands of entries, just one calculation and one jump. That's why lookups are so fast. The position isn't found, it's computed. But here's the catch. We have far more possible keys than buckets. So sooner or later, 2 different keys will hash to the same index. Amit maps to bucket 0, and so does Ravi. That's called a collision. It's not a bug, it's expected. What matters is how the hash map handles it. The most common fix is called chaining. When multiple keys land in the same bucket, the hash map simply stores them together, usually as a small linked list. Now bucket 0 holds Amit and Ravi. On lookup, it jumps to the bucket, then walks the short chain, comparing keys until it finds the right one. This is exactly why we stored the key alongside the value. And in modern implementations, like Java's HashMap, if one bucket's chain grows too long, it's converted into a balanced tree. So even heavy collisions stay reasonably fast. What if we insert the same key again, say Amit's marks improve to 96? The HashMap hashes the key, finds Amit already in that bucket, and simply replaces the old value. Keys in a HashMap are unique, same key in, the value gets updated, never duplicated. Deleting works the same way. Hash the key, jump to the bucket, find the matching key, and remove that pair. Notice the pattern. Insert, search, update, delete. Every operation starts with the same 2 steps. Hash the key, jump to the bucket. So how fast is all this? On average, insert, lookup, and delete are all O of 1, constant time. It doesn't matter if you store 100 entries or 1,000,000, it's one hash, one jump. But there's a worst case. If a poor hash function dumps many keys into the same bucket, lookups degrade toward O of n, because now you're scanning a long chain. In practice, good hash functions spread keys evenly. Occasional resizing keeps buckets from overcrowding, and tree-based buckets soften the worst case. That's why hash maps are fast in the real world, usually. Here's the everyday version. In a library, you don't wander every shelf looking for a book. You type the title into the catalog and it tells you exactly where to go. The title is the key, the shelf location is the value, and the catalog is your hash function. That's a hash map. Don't search. Compute where to look. Using one is even easier than understanding one. In Java, create a hash map, put Amit with 92, put Priya with 88, and get Amit outcomes 92. In Python, you've probably been using hash maps all along. They're called dictionaries, and they work on exactly the same idea. Same concept, same speed, slightly different syntax. Quick recap. A hash map stores key value pairs. A hash function converts each key into a bucket index, which makes insert, search, and delete constant time on average. Collisions are normal and handled by chaining, or trees when things get crowded. One last detail. A hash map doesn't promise to keep your entries in order. It promises speed instead. And that trade-off is why hash maps power caches, databases, and half the code you'll ever write. If this made it click, subscribe. Next up, we crack open the HashSet.